Hey guys, and welcome back. Since I wasn't going to see you today in the building or on Zoom, I wanted to just have a little bit of a conversation about where we're at with velocity versus time graphs, just try to summarize concepts that we have seen in the practice, and then also to move into starting to talk about kinematics equations, so we'll see that as well. So first things first, when we summarize what we know about velocity versus time graphs, we can go back to the same three questions that we've been talking about all along. And first one was, which direction is it moving? So if we're looking at a velocity versus time graph, we want to know, is the velocity positive or is the velocity negative? So the way to know that is to know if the graph is above or below the t-axis, all right, your horizontal axis. If it's above 0, then it's moving in the positive direction, and if it's below 0, then it's moving in the negative direction. If we want to know how fast it's going, the question to ask yourself is, how far is the graph from 0? Because remember, 0 is the slowest you can possibly go, 0 meters per second, and that's in the middle on the horizontal axis. So the farther you are away from 0 meters per second, the faster you're going, whether in the positive or the negative direction. And then, is it changing speed or direction? Well, that depends on if the graph is flat or not, because we're looking at a velocity versus time graph. So if the graph is flat with 0 slope, then that means the velocity is not changing. If the graph has a slope, then that means it is changing its velocity, it's accelerating. And in fact, if the graph crosses the axis and goes from one quadrant to another, for example, from the first quadrant to the fourth quadrant, or from the fourth quadrant to the first quadrant, then you have a change in direction because of what we talked about in that first bullet point here. So overall, the slope of a velocity versus time graph tells us about the acceleration. When you have 0 slope, you have 0 acceleration. And the steeper the slope is, the bigger the acceleration value has become. So just a way to remember what we've done over the past few days. So next we're going to get into some kinematics problems using equations of motion. And first I just wanted to go through some basic problem solving steps. So the first thing you want to do is, read the problem very carefully, make sure you understand it, and then, reread it. Figure out what object you're talking about or objects in the problem and what time interval over which you're studying them. Sometimes it's a good idea to draw a diagram or a v versus t graph and choose coordinate axes, and we'll see examples of this in a bit. We want to make a list of all the known quantities and then the unknown ones that we're looking to find. Then you want to think about what physics applies here. What approach do you want to use to get to the solution? So which equations relate the known and unknown quantities, and are they valid in this situation? Then you want to solve those equations algebraically first and make sure that the units match up. It says correct dimensions. It's the same idea. Calculate the solution and round it to the appropriate number of significant figures. Then look at the result. Is it reasonable? Would it agree with a rough estimate? So you want to think about, does this answer seem to make sense? And then check the units again. This is just a quick summary of the different quantities that we talk about when we're studying kinematics. So we have displacement, velocity, acceleration, and time. Those are really the big four when we're talking about kinematics. So displacement, we're going to use the symbol delta x, and that's how much something has changed its position. The standard unit is going to be in meters. V is going to be for velocity, and that's going to be measured in meters per second, although you could measure in miles per hour, kilometers per hour, or feet per second. we're going to use the symbol A for acceleration, and the units are going to be meters per second squared, and then the symbol T for time, we'll use the lowercase t, and the standard unit for time is seconds. Obviously, you can measure time in minutes or hours, but seconds are going to be the standard unit. Okay, and then these three equations you want to definitely write down. Get these in your notes because we're going to see these lots of times over the next several days. But these are three of the principal kinematic equations that we're going to be able to use to solve problems and make predictions about the motion of an object. So the first one is Vf equals Vo plus At. So that's the final velocity equals the original velocity plus the acceleration times time. The second one is delta x equals Vot plus 1/2 At squared. So this is your displacement, your original velocity times t, 1/2 the acceleration times t squared. We only square the time in this equation. And then the last one I like to call the no time equation. So this is Vf squared equals Vo squared plus 2a delta x. So final velocity, initial velocity or original velocity, acceleration, and displacement. So later on in the video, you're going to see how these are connected with the graphs of motion that we talked about previously, and eventually start to see solving example problems using these equations. Alright guys, so since we are asynchronous today, I wanted to take some time to talk about constantly accelerated motion and really try to connect what we talked about with graphs of motion with the equations of motion which I introduced to you at the end of last week. So let's start by considering a situation where you have an object that has a constant acceleration, and let's assume that that acceleration happens to be positive. Now, we haven't talked about acceleration versus time graphs yet, but I think you could figure out, you have enough knowledge at this point that if we were going to graph acceleration versus time, and we're talking about something having constant acceleration, and it's positive, then the graph is going to be a horizontal line above the t-axis. So we're just going to have a horizontal line indicating we have constant acceleration. It's not changing its acceleration, and it happens to be some positive value. Okay, so that's pretty straightforward. Now, imagine what a v versus t, a velocity versus time graph would look like that indicates the same thing, that indicates constant positive acceleration. Okay? Let's assume for a second that it starts at some positive velocity and it has a positive constant acceleration. All right, if you think of the modern Galileo labs, a good example of this, the graph would be a linear graph. And since we said it starts with a positive velocity, I drew it above the t-axis and with a positive slope indicating that it is accelerating in the positive direction. Okay? Now, imagine what a position versus time graph would look like for this type of motion. So if an object starts out at a low velocity that's positive and gets faster and faster in the positive direction, we should expect that it would curve opening upwards like this. Okay? So I don't think that the shapes of these three graphs are all that surprising. However, let's think about this. This is a straight line. You guys know from algebra that a straight line has the equation y equals mx plus b. Okay, but think about how that general equation applies to this specific instance. In this specific instance, the y-intercept of the graph is the starting velocity. So this is the original velocity. The slope of this graph is the acceleration. And what we have on the x-axis is time. What we have on the y-axis is the velocity. Sometimes we'll put v final. But this should look familiar. This is one of those three equations that we introduced on Friday. All right. Any object that has constant acceleration is going to have a velocity versus time function that's linear. So that's where this comes from. We can rewrite it. Like I said, sometimes we'll use the subscript f. So we can say vf equals vo plus at, like so. Okay, now, this function is a curve. Some folks would say, oh, it's an exponential function. Turns out it's not exponential. It's actually a quadratic function. Okay, if you remember what a quadratic looks like, the general form of a quadratic is ax squared plus bx plus c equals 0. Okay. In this particular situation, all right, what we're plotting on the vertical axis is position. What we're plotting on the horizontal axis is time. So we can replace the x's with t's. All right. And it turns out that the specific equation that fits this scenario looks like this. I'm going to try to squeeze it in here. AT squared. All right, so that says x equals x naught plus v naught t plus 1/2 at squared. This is a quadratic function, and if we subtract x naught from both sides, we could rewrite it in the form we saw it in class, which was delta x, the change in position, the displacement, equals VOT plus 1/2 AT squared. Now, for those of you that are in calculus, you could prove, for example, that the derivative of this function gives you this. All right, the derivative of this function gives you a constant function, or you could integrate and work backwards. So the integral of this gives you that, and the integral of this gives you that. Again, you don't need to know calculus to be able to do AP Physics 1, but having that knowledge isn't, certainly not going to detract from your understanding. Okay, so this equation here and this equation here both describe position or velocity of an object as a function of time when it has a constant acceleration. In fact, we could go back and model these equations to the modern Galileo lab and see why a quadratic fits in the position versus time for the bowling ball, or a linear function fits for the velocity versus time for the bowling ball. Now, you also saw a third equation in the notes, and that one looked like this. VF squared equals VO squared plus 2A delta X. I like to call this equation the no time equation, because if you look at it, out of the three, it's the one that doesn't have a t in it. Where this comes from is just algebraic manipulation. Okay, if we solve one of these two equations for t, and then we substitute it into the second equation and rearrange it, we end up with this relationship. So this is helpful when we have a situation where we need to know how fast an object is moving when it's at a certain spot, instead of how fast it's moving at a certain time or where it is at a certain time. This one takes time out of the picture and allows us to look at it from a different perspective. So I wanted to give you this heads up so you can understand a little bit better where the equations of motion came from and be able to connect them to the equations and being able to, or connect them to the graphs, I should say, and be able to put those two together and help reinforce your understanding.